before we get down to how WebGL does texture mapping, and let's talk about some general approaches to the problem and where it'll give us also an idea of where the difficulties arise. So what we're going to look at is forward and going backward, the coordinate systems that are going to be involved, and issues that involve the potential for aliasing when we sample the texture in order to get a color to apply in our case, within the fragment shader. So let's look at the following. Here's a really simple idea or map picture of what we're trying to do. Suppose we have a two-dimensional picture and we want to map it to this curved surface in 3D. Okay, so you can think of it as curved, and even though underlying it is a bunch of polygons. So at first it seems a fairly straightforward thing. It goes on there very nicely. But let's look at all of the coordinate systems that might be involved in doing this kind of a mapping. Okay, so first, if we used some sort of parametric form for the curves and surfaces, then there are parametric coordinates involved. So for example, if this were something like a Bezier patch or a quadric, it would be each point on the surface, the x, y, z, would be a function of two parameter values that we'll later call u and v. But we've seen some examples of that already. So that's going to be evolved. That we let u and v go over some range, and that then gives us the locations of x, y, and z in the object coordinate space. Okay. Then we have to identify points within the texture. So what are we going to do for that? Well, the textures we're going to be dealing with are two-dimensional. So we'll have a two-dimensional coordinate system within that texture. They'll be called ST coordinates by convention in here. So we have so far two coordinate systems, neither of which are the coordinate system that we actually work with in terms of the geometry or the coordinate system that we display. Oh, by the way, before I go on, let me point out that WebGL only supports 2D texture mapping, but we're going to see more possibilities in the near future. Desktop OpenGL supports 1, 2, 3, and 4-dimensional texture mapping. So one-dimensional texture mapping might be something like a line that had a texture pattern on it that we would then map into 3D space. A 3D texture would be something like a block of granite, and it would have all of the characteristics of the granite and the different colors inside of it, and they would be specified by 3 coordinates and then would be mapped over to 3D. 4D texture mapping is kind of weird, but possible. But also note that all of this fits in with the geometry pipeline, which is always operating in 4D. So anything we do with geometric coordinates, turns out we could also do with texture coordinates, and we'll see some more of that sometime later in the class. Okay, now what else do we have? We have object coordinates, because this surface exists in a 3D space, so we have our modeling space or world space that we have to worry about. And finally, at the end, we are going to have to worry about the coordinates of the pixels, because for each pixel we're going to have to assign a color. So if we look at it slightly differently, then you see a picture that looks like this. Here's a forward-looking view. It says, okay, take a point over here in parametric. Oh, well, let's do it this way. Take a point here in parametric space. So for every u and v, you're going to get a point on this geometric object. So there's a mapping of u and v to this surface for x, y, and z. Now, we've seen that before. Now we're introducing this texture, which, even though s and t will vary over this rectangular space, and by convention will make this go, s and t both go from 0 to 1, it's not necessarily related in any obvious way to this UV little rectangle. So we have a separate space here that's getting mapped over into world coordinates, but it tells us there's a point here and a point over here that when I figure out where that x, y, z is, I can in principle figure out which point back here in ST space is going to give me the color I want, and then eventually this is going to go through the pipeline and be mapped out into screen or window coordinates where we'll have XS and YS. Well, that's just a nice theoretical view, but I could have just as easily, and we're going to see this, said, well, what if I started over here? And I said, well, here's a point in screen space, okay? There's a texel over here, excuse me, there's a fragment over here, and I want to find its color. How do I find its color? I could actually go backwards. I go say, well, where is it in world coordinates, and then what texture value does that point in world coordinates correspond to? So there's this idea that you're doing some forward mapping, but yeah, you might also want to do some backward mapping, and how do I find these maps, and often ask the question, do they even exist? Another factor that comes up, you can see sort of here, is that there's shape changes. That you have a nice little rectangular area here, but when that rectangular area is mapped onto the surface, it's not rectangular anymore. It's a curved shape, and that, as we'll see, complicates matters too. So these mapping functions exist in principle, and in principle you'd sort of like this idea that for each x, for each s and t, we get a particular value on the surface. Unfortunately, we want to go in the other direction, and we start in the fragment shader, and we want to go backwards to find out what the appropriate texture value is. So given a texel or a fragment, which point on the object does it correspond to, and then from each point on the object, we want to know what texture point it corresponds to. So he's sort of implying that there are two maps, a map from screen space back to XYZ object space, and a map from object space back to texture space. And that's unless you have special cases, that's really difficult to do, and we got to figure out how to get around that problem. So here's a sort of a traditional way people did this. They used what's called a two-part mapping, and we'll actually see that when we start talking about cube maps a little later on that actually use the same idea. So what we do is say, well, if I had some simple objects, I could do it. So for example, if my image was like the label on a soup can, that's always an example people use, it would be this nice rectangular area wrapped around a cylinder, and that's a very easy map to do, and I could combine that with a very simple parametric model of the cylinder. If you give me the radius of the cylinder, then the height just goes up linearly with one variable, and then v and the other variable u, then I could use for each plane of constant z get a circle. So that's pretty easy to do, and then I could just say, well, in that case, then just make the texture values the same as the parameter values, which gives me one particular way of doing that. Likewise, if I used a sphere as the intermediate object, I could use the sort of the longitude and latitude model of the sphere, which again is a two-parameter family. You can use u and v again here, and that for u and v, one of them going through 0 to 180 degrees and the other going through 360 degrees, you get all the x, y, z values of the sphere. Now this is fundamentally different from using the cylinder. If you look at the cylinder, let me come back one more. If you look at the cylinder, there's really no real distortion that goes along when I wrap this rectangle around the cylinder. We're ignoring the top and the bottom. However, we know from previous discussions that when we map something that's flat to a sphere, or a sphere to something that's rectangular, there has to be distortion. This is generally the mapping problem. So when you look at, say, the standard Mercator projection, you see this tremendous distortion at the poles, where Greenland is enormous and Antarctica is enormous, because you decided that, well, we can put our distortion up there. And there, for that particular mapping, there has to be distortion somewhere, and we get to choose where we place it. So sphere mapping is important. We'll see some examples of that when we get to environmental maps. It's supported directly in desktop OpenGL, and so we'll see more discussion of that. But probably a more useful one is this one, where we map to a cube which can be unfolded. Think of it like a cardboard box, and we unfold it so you have the bottom attached to the left, right, front, and back, and then the top is on the right, and that folds over the top. And that's fairly easy to map. It also works well with the standard projections. So the three standard intermediate objects to use are cylinders, spheres, and cubes, and they all have the property that if you have that, it's pretty easy to map them onto the surface. The difficulty is, how do you get to the sphere and the cube and the cylinder from the actual space? So how do you get from a real object? So we're looking at a top view, sort of a 2D picture, and say, here's the surface of that object. I know and this is using the sphere, or actually this could be inside a cylinder too. How do I get from this object to points here? I know how to go from points here to map to a texture, or a texture to these points. So there's sort of three basic ways you can do it. If this is circular, then I know how to easily can compute the normal here, and then I just follow where the normal hits the object, and that gives me an x, y, z value. I can also go the other way. If I can look at this surface and I have, backwards, sorry, and I have the ability to model the surface or know it analytically, I can compute the normal or the tangent over here and then go out from here to a point on the surface, and that'll give me a value of the texture. So the assumption here is I've mapped the texture to this intermediate object. Now I can then project down here to place that texture on the object, or I can go from the object out to the sphere or the cylinder and then get the texture value. And notice it's giving me a very different value in these two cases. Or I can go to the center and simply draw lines that go out radially from the center, and then I could follow, here's a color where it intersects the object, and then follow that color out to, or follow that line from where it intersects the object out to the surface of the intermediate object and get the color from over there. And that gives me a different value than either of these. So we can, do this in various ways in principle. Now, the next issue is what happens because everything's really discrete. And here's one example of that, where if we're doing what's called point sampling, that somewhere how you go from XYZ space to texture space. Let's not worry about which method we're using, but the problem here is that because you're doing point sampling, for every point here there's exactly, on the object there's exactly one point over here. So if you think of this object as being ruled into pixels here, or this could be, interpretation is exactly the same if we look in parametric space, that there's one, that the parameters as we go discretely in U and discretely in V, and we take a point at the center of for each UV, and we map that back over here to the texture to find the texture value. Well, the problem is, look at this sort of rigged aligning, but you have the problem anyway, is it's completely missed all the blues. So what we see now in this extreme example are just the whites here. Now, even if it could conceivably, if I changed it a little bit or went down to the next line, I may only hit the blues. Well, that's not going to give me what the texture really looks like, and the issue is that this is an aliasing problem that, there's an appendix on aliasing which talks about aliasing in general, but basically any time that you have discrete values that are coming from some continuous space, you're going to not be able to capture it exactly and have to make certain assumptions. And point sampling will give you, at least visibly, the worst aliasing kind of errors, because this kind of thing will lead to a lot of jaggedness. So a better way is to use some area averaging techniques. So here we assuming we can do these maps, start with a pixel in the frame buffer, and map that back to the object. Now notice that that now gets mapped to some curved area on this curved surface. That's called the pre-image of this pixel. See, generally we're going forward, but if I say, well, look at this from the point of view of the fragment shader. The fragment shader's got a pixel which corresponds to a rectangular area. What does that correspond to in object space? Well, in object space, it corresponds to this curved little piece of the surface called its pre-image. Now I could, at least in principle, map that backwards and say, that maps to a little curved area in the texture, and I could now do something like sample this multiple times or integrate over this little area to get a better value for the texture, which I could then go forward back to the object space and then on to a color for the pixel. Well, in principle, that all sounds nice, but it's very, very difficult to do for anything but the simplest problems because we simply don't know those mappings. So what we're going to do now is turn to how WebGL does it, and which it works very, very well in practice, but forces the application programmer to essentially specify what these mappings are.